if you don't have a raffle ticket, my friend Peter here with a red roll of tickets is going to pass out the tickets. So if you need a ticket, raise your hand. Petrovich. Okay. Pete's ready. Raise your hand if you want a ticket.
Remind them they took both pieces.
If you took a ticket and put both of them in the can over here, or kept them, you only put one in the can and keep the other one. So if you need to redo, come on down. But you can only do that before the drawing, not afterwards. We're about ready to start the meeting. So if you're up having coffee, bring your coffee down. Otherwise, almost ready to roll.
I'm the focus for some reason. Crazy.
Okay, let's make the Barbara.
Okay. Welcome everybody to the July meeting of Orange County Astronomers. Folks in the auditorium, I hope you've got your drinks and your donuts and are finding your seats. If any of you have not got a raffle ticket yet for the telescope that our speaker was kind enough to bring tonight to raffle off, please, there's a gentleman up at the back who has got the tickets. Please contact him, put your hand up, he will get you a ticket. And we will be doing the drawing after the announcements. And let me see what else. Oh, yes, we have our annual star party coming up. Our annual Starbecue at the star party at ANZA. So if you are thinking about going out to ANZA for the July star party, bring a dish along. Join the fun up at the observatory. We'll be meeting behind the observatory where there's shade. Which if you've been out at ANZA at this time of year, you know, is a welcome commodity. By the way, if you're wondering who I am, I'm your current president. I'm Barbara Toy, and we have a full roster of fun and games tonight. So I think with no further ado, I will turn this over to Kyle, who will be doing tonight's announcements. Giving it to you, Kyle.
Perfect. Right. Here we go. So welcome new members. If you just joined, your membership badge will be on the whiteboard there in the auditorium. If you're not attending in person, in a couple months, those badges will automatically be sent to your home address. I'm sure everyone in the auditorium already knows about the coffee, donuts, and water that are available for purchase. Hope you're enjoying them. As mentioned, the ANZA Starbecue Star Party is July 26th. Astrophysics will be meeting on July 18th. Astro Imager is September 5th. And the next board meeting is July 13th online. The next beginners class will be August 1st at 7:30 p.m. at Orange Coast College. and it will be on the basics of astrophotography. Upcoming event, the 2025 Mars Society Convention is occurring at USC, October 9th through 11th. They've lowered registration rates this year. The early bird rate has already ended, but there is a student and senior discount. You can see the information here. And if you're a member of the Mars Society, you can get a special member rate. You can find more information about the event at the website there below. The Adopt Scope program is up and running. You can see how to get to the information on our website, where you can see what the programs, how the program works, sampling of the current inventory we have, along with the sample adoption agreement. Our outreach events coordinator is Martin Christensen, and please reach out to him if you are willing and able to volunteer at any of these upcoming outreach events. They're always a fun time, so if you're available, please join.
Kyle, just a second. For those that are in the audience here, Martin is here. He just raised his hand. If you'd like to talk to him about the outreach program, this would be a wonderful time to do that. And back to you.
Dave Fisher is the editor of the Serious Astronomer, and he is always looking for content to put in the newsletter. So if you have anything such as articles, images, trip reports, equipment for sale, etc., that you think would be a good fit for the newsletter, please reach out to him and he can review those items. Reminders that if you're out the ANSA site and you're the last one to leave, make sure the ANSA house is all locked up and the windows are closed, and that the gates of the site is closed when you leave. Also, please remember, if you have a pad out there, to help keep weeds clear. And if you can help in the common areas, such as around the ANSA house, football field, and the observatory, that would be very much appreciated. The next general meeting is August 15th, and I will turn it over to Chris Butler for the What's Up presentation. Thank you.
Right. Hi, everybody. I'm Chris Butler. Going to talk a little bit about what's going on in the sky this month. And let's see. Oh, yeah, all right. Here we go. I think we're all set. Let's leap into it. First of all, starting out with the sun this time of year, we still have a lot of sunlight at this time of year. Sun's not going down till 8 o'clock in the evening. So that's very nice for us. If we like the day. However, we are nocturnal insectivores ourselves, and we prefer to hang upside down from the rafters and make squeaking noises, being astronomers. So I understand you want the longer nights. However, if you've looked already in a Michael's, you know the Halloween decorations are already out. So you know it will not be long until autumn arrives. So we'll get through the rest of the summer. The nights are a little bit longer every single night now. Looking at what's going on with the moon, I'm a big moon fan. We just had a full moon on July 10th. Tonight, we're just past that, so the moon's rising later and later and later. We will get around to last quarter phase on July 17th, when the moon rises at midnight. Half-lit moon that you see in the pre-dawn sky, and then swinging around to the dark of the month, dark of the moon at the end of the month. July 24 will be the dark of the moon, new moon. Running through the planets, we got Mercury in the evening sky. Again, some charts and maps to follow. But Mercury, if you're a fan, evening, okay, you can catch it. Obviously, do wait for that sun to get all the way below the horizon, because although California is the most litigious state in the universe, I'm sure you will not be allowed to sue for your burned out eyes if you attended the What's Up lecture. And I warned you, don't look at the sun with a telescope. So Mercury's in the evening. Venus, however, very much not in the evening. That's a morning object. You got to get up early for that. Rises 3 o'clock in the morning in Taurus. Mars is, though, an evening object, not too far from Mercury, map to follow. It isn't setting until all the way about 10:55 p.m. It is not, however, blazingly bright. It is not, however, looming as large as the full moon in your telescope. No one alive today will ever see this again. I'm just teasing you, all know that comes around every year. Boy, that's not coming around now. No, it's playing It's a Small World. It's only 4.7 arc seconds across in your telescope. Jupiter is magnificently bright. However, it is not magnificently placed. It is rising right before the sun. You can detect it because it is so bright down on the horizon. However, it's just not a good time. It's still down in the murk. Give it a month or two and you'll see it better in the morning, pre-dawn sky. Saturn is rising just before midnight. 11:41, transit time around dawn. So if you're up in the pre-dawn hours, Saturn should be good for you. Uranus also in Taurus, as is, for example, Venus, meaning it's a morning object right now if you want to catch it. Neptune, interestingly, if you haven't caught it before and you'd like to catch it this time, Neptune has the convenience of being quite near Saturn, meaning behind it. Saturn is naked eye bright, where Neptune requires a telescope. So if you haven't seen it before and would like to hunt it down, Saturn points the way. Pluto
Chris,
included.
sorry to
Yep.
interrupt.
Go for
we're
it.
not seeing the full screen presentation, Alan, if you can.
Oh, well, it looks totally different if it goes full screen. Yeah, this is like those the old CinemaScope movies I used to watch on TV, and you could only see part of it. So it's technical staff is working right now to address your projection problem. We want to make sure, especially for the charts that follow, we want to make sure you get the port and the starboard in addition to the amidships view. So just one moment, please. Hey, for the old timers, it could be worse. It could be live from Anza, right? You want to be generous with your time while you're waiting for a technical fault to be solved while staring at somebody's rear end in the middle of a blurry camera view. Trust me, no, this is fine. Well, this will be just great. All right. All right, just a moment. Thank you for pointing that out, Ressa. Sorry about that. Uh-oh, I think we may have solved the. No, we
Okay,
haven't.
you're seeing the presenter's view now.
Okay, he's. Well, you know it's bad if I start looking to see if we have dry erase markers. I could actually just draw the rest of the scene on each side of the screen. That would be great. Just imagine what the rest of it looked like. Really? Okay, no, we're cool. So how y'all doing? You know, I came to this astronomy club to meet girls. I swear to God, I did. Yeah. Coming around that door right there, I took one look and I knew it was over. Yeah. Oh yeah, yeah. Well, yeah, because standing right about where that lovely telescope is was John Sanford. So, what do you want, kid? You're probably here to meet girls, aren't you? I said, no, John, I'm here because I love
Okay,
astronomy. Are we all set?
Yes.
Fantastic. All right, let's leap right the rest of the way. We're talking about Pluto. It is near the moon tonight, if you wanted to get something to give you a clue where Pluto would be. The easiest way to find Pluto is to get near Pluto and then lie about whether or not you saw Pluto. Just pick any star. Just say, well, there it is. It's the one with the moon next to it. Look, there's Charon, there's Pluto. That's what I've done for years. Talk about something you're probably not going to get to see, but you've heard about in the news, which is, of course, the potential interstellar comet, which coming through our solar system at very high speed. Yes, it's been detected. Yes, it's a real thing. However, number one, it's not here yet. We're getting questions about this at the observatory all the time right now. But it will not be around until later in the year, and it's not going to be especially near us, and the estimated highest magnitude 11, something like that. We'll see, but it won't be here till the end of the year. However, next year, when their battle fleet arrives, there may be some excitement at that time. Not speaking legally for the city of Los Angeles at this time. This view here shows the planets which are around the sun right now. The planets you can see off to your right on the screen, Jupiter and Venus, are in the morning sky. Okay. And then the planets Mercury and Mars that we see over on the left side of your screen, those are in the evening sky. So this actually gives an overall view of where the planets are with respect to the sun. But if you leap to a view like this of the entire sky, just of course a map, it gives a sense now of what you're really looking at. You just have to peek over the edge of the Earth with the Earth blocking the sun so things get dark. You can see half of the picture around the sun. In this case, Mercury would be rotating around and setting in the west-northwest pretty quickly after the sun goes down, so it won't be very high. Mars also is not very high, so it too is on its way down as the evening gets dark. Notice that there really are not any other planets around at this time. The very sharp-eyed people could notice in the east that the moon in this map is just on the horizon, about to rise at this time. This is the map for tonight. Constellation that I've picked for you to look at this time is Draco the Dragon, one of my favorite constellations. It is very, very, very far north, has an interesting potential to cause a fist fight at your astronomy trivia night. Notice, although it is not the largest of constellations, it is not. Hydra is, I believe, the absolute longest in terms of linear length in the sky. This one wraps around the celestial pole very close to the pole, which means it can make many of those grids it spills around like hours of the clock, well, hours of right ascension. It covers, in fact, very nearly 12 hours of right ascension. If it were on the equator, it would be an absolutely ginormous constellation. The only way the Dragon gets away with this is by being right around the North Star. It's very close to it. Some hack did a picture of what Draco the Dragon would look like if you have a lot of imagination and maybe, you know, some pharmaceuticals. I don't know how you would get a view like this. But you could see it different ways depending on what you're trying to do. This is the way it was represented in 1825 by Sidney Hall, famous set of astronomical postcards of the time. Notice it has not eaten a raccoon. That is instead Ursa Minor, the little bear with its long nuclear mutated tail. But that is the little bear whose tail is the North Star Polaris. Other ideas for what Draco could be, the shape is pretty distinctive. It could be a saxophone. Thank you, Chuck Edmonds of our own club. I can't unsee that. And then it could be that other thing, which is too horrifying to contemplate. Zooming in a little bit here to look at Draco more seriously. The brightest star in the constellation marks the head of the dragon. Eltanen is the star, if you know your Greek letters, and I'm sure we all do, is Gamma Draconis, right? That's the third letter of that alphabet. Clearly, this is the brightest star, but it got the Gamma designation, not Alpha. Did not get that. Usually the Alpha star is the brightest star in a constellation. However, in this case, it was the most important, historically important star in the constellation, which is the star Thuban, has the label for Alpha. And that's way off in the Dragon's Tail, not far from the Big Dipper asterism in Ursa Major. Thuban's kind of a silly name, kind of a fun name. It's easy to remember. I've hunted down this star a few times because it is an X-pole star. This is the easy way to remember it for people of a certain age. Thuban just sounds like U-ban, and like U-ban, it will be up all night. The historical time period when Thuban was closest to the North Celestial Pole was approximately the time of the ancient Egyptians. A lot of people think that the pyramids, some of the pyramids were actually aligned to the passage of Thuban. So pretty cool. Here is an annoying picture because it's one of like 3 or 4 or 5 that are always on TV, really famous celestial objects, like in the old days when we'd have open slides in here. If anyone even remembers open slides, and people would show their astrophotographs and they'd be like, M51, M42, M42, M51, M42, M51. I know the Whirlpool Galaxy, I got it. This is like that. It's got, well, they got a good agent. That's just that simple. They get a lot of press. This is the Cat's Eye Nebula, a so-called planetary nebula gas cloud blown off by a dying star. It is in Draco. It's one of the bright examples of this type. But this nebula, the Cat's Eye Nebula, this image is so often shown, you may expect it to look like this through your telescope. That could cause you to harm or injure your telescope. So let's not do that. Let's show some different pictures of the same exact object. This is a wide field object shot by the incomparable Adam Block, Mount Lemmon Observatory. This is a wide field picture. And if you were to look very, very closely, the exposure is so beautifully done on this, you actually can see in the center of the picture a little tiny version of the picture you saw from Hubble. It's in there. Those details are in this picture. But there are these outer gas shells that have been blown off as well that are much fainter. Now, it's a long exposure photograph. This is not what it looks like to your eyes. And we as amateur astronomers also have the experience of seeing it with our eyes. And that might look something more like this. This is an example of a sketch made by an amateur astronomer. And you can see how wildly different this experience of the same exact object is, whether you're looking through a giant space telescope on the evening news, that picture, or taking a long exposure photograph, or here, the experience of just seeing it with your eyes. Now, Draco has a lot of different things that you could look at. This beautiful galaxy, Edge-on Galaxy, NGC 5907, I think probably the premier galaxy in Draco, but I'm going to show a couple of others as well, including really obscure stuff. And the reason I do that is to make you think I know what I'm talking about, okay? So, and actually to please one person in the room who's fond of ARP galaxies. So here's some other NGC objects, another edge-on and a face-on spiral there. Here is yet another galaxy, a pair of galaxies, close interacting pair. And here we go with yet more exotic and strange galaxies. I love these pictures. The colors are very good in these, I think. I love the range of colors in the stars, especially. ARP 30. That's an example of an ARP galaxy cluster. And then ARP 293. I know. You're going, why are you just showing the obvious stuff? Show something exotic, right? But obviously, this is a place that's good for looking at galaxies, and there's lots to look at here. Let's go ahead and wind out your evening now. You've been looking at Draco there for 3 hours since our last slide at 9 o'clock. Notice it makes such a small circle around the North Pole, the top of your picture there, that Draco at midnight is still up. Last map I'll show you is at 5 a.m. when the sun's getting ready to rise and Draco is still up. So you can take your time with a circumpolar constellation like this. Notice the moon is down there. I promised you near Pluto. But if we give some more time here and let Saturn come up, you will see Saturn and Neptune next to each other, Moon getting ready to go down. This is as the sky is getting light. And there's your parade of morning planets. Uranus is there. If you want to try with a telescope, Venus and Jupiter, brilliant, but not very high up in the sky, really, at dawn. Do want to spend some time just with Saturn over the next few days, if you can, though, because there's something really neat happening. Notice Ceres, by the way, there. Stop by and check out the asteroid Ceres if you're in the area. We have a Titan shadow transit. These don't happen all that often. I believe it's about every 15 years. We'll have several of them in a row. The notes there are from Griffith Observatory Sky Report. We have one coming up on the 17th of July, 11:43 p.m. is when it will start. So you're going to be up fairly late. This is when Saturn's largest moon will drag its shadow across the face of Saturn. Should be a really neat show. These do happen in groups, like I say, about every 15 years. You can see some of the ones labeled here from this group, not that next one. They didn't list the July 17th one in this illustration from Sky and Telescope, but it's well worth your time to have a look. They're pretty spectacular events. With that being said, I wish you dark skies in LA. We don't get many of them. This is the only scenario where you will get dark skies, which is to say a gigantic earthquake that blocks out all the power and we're plunged into blackness and everyone else will run around screaming. We will all run out with our telescopes and have a lovely evening. Thank you for your time and attention and your patience with technical problems. That's it.
Raisa, before we get to the speaker, I think we should probably have our drawing for the raffle.
That's right.
Okay. Is there anybody that did not get a raffle ticket that wants a raffle ticket before we do the drawing? I'm not seeing a forest of hands. So I think that perhaps our speaker should be the one with the honor of drawing the winning ticket. Okay.
Does that mean you get to read it though? Because in
well,
the
yeah.
dark. So, somebody. Oh,
You want to read it off?
certainly. Okay, let me not blind anyone with my pointer. All right, do you all have your tickets? Hold them up. Yeah. Got them out. Get them out. All right. The numbers start 668. Any winners? Any winners? Okay. Followed by 797 and the winning last digit 7. So the full number 668 797 7, and we have a winner. Come on down. Come on down. Yeah. Oh. Normally that. Congratulations. Oh, yeah.
I'm Brian Hansen.
And how long have you been a member of?
Oh, gosh, I started in college. Yeah. Time.
Good things come to those who renew. That's right.
Okay, yeah. So are we ready for the introduction of the speaker or?
Yes. Yes, go ahead. We have a winner for the telescope, and the speaker is now really ready to turn his attention to the other business of the evening for him.
Okay, great. So our speaker tonight is a retired physicist with over 30 years experience in aerospace industry doing design, development, and testing of imaging systems and sensors operating in the visible, infrared, and radar spectral regions. He has been a member of the OCA for 1 year and is currently building a backyard radio telescope. Please join me in welcoming Steve Hallman. Steve.
Share screen.
Great.
Is it good?
Yes, good on our side.
No, I actually too much energy. I got to move around. So, and you'll be flipping my sides for me. All right, which is just press the space bar. Okay, I've got you all. Son, hello. Can you all hear me? I'm loud. I can yell louder if you need. And I went out and indulged myself and got this really cool laser pointer. So I have something to point at my charts with. And a moment while we optimize the view. Sweet. That's good. What? I'm sorry? Hello? We're good. Hold on a moment. Let me go out. Few words. Next slide, please. All right. Okay. Can they hear me because of this? Okay. All right. Can everyone hear me? Good? Yes? All right. Sweet. All right. So tonight's presentation is on backyard exoplanet observatory. So for those of you who have ever thought, maybe I'd like to do something in exoplanets, they're kind of cool. You hear about them periodically. You know, it's where those aliens live, where maybe someday we're going to hear about. And so, but where you usually hear about them, you know, they're being done at Palomar or some, you know, telescope on Mauna Kea or somewhere way down in Chile. Well, you can actually do some stuff with a very small telescope. In fact, this telescope, more than you need. So I'm going to show you actually doing that. Next slide, please. Ooh. No? All right. How about the left arrow or the right arrow? Will that do it? That's special. How about a click? No click. Okay, this is special technical issues. Wow, I can't even exit.
Do you happen to have annotation on?
No, I don't believe I do. But there's an overlay.
Yeah, there's an overlay. We see a line just pass through. Looks like
Yeah,
that's
and
maybe escaping and resharing.
escape doesn't even get me out.
Seems like it's locked up.
Doesn't think that. It is.
Okay, but we have the line sting through your presentation. Looks like there's another software doing the overlay.
Reza, he's backstage.
Okay. And you need to disconnect audio, Steve.
Oh, yes.
Okay, looks like it's working on our side.
Hello? All right. I think we're back and live this time. Okay, that was our one technical glitch. Make a note of that. All right. All right, let's start with the basics. What are exoplanets? Well, that's what you find when you Google, right? You Google in, you put that word, what is an exoplanet? And it comes up with a whole bunch of stuff. And by the way, it sends you to a NASA website too. This is so you can download all these. NASA has a bunch of free posters of travel posters of what would it be like to travel to various exoplanets. So I've downloaded several of them, and you'll see them here. You can just Google, go to the NASA travel exoplanet poster thing, download it. Makes a great screensaver or a desktop thing. So, all right, an exoplanet is any planet that is not orbiting our star. So any planet around another star is an exoplanet. They're currently confirmed over approximately, not actually slightly under 6,000 exoplanets by NASA's count as of today. Big bulk of those are from the Kepler mission. And so, and they're found, I should say, by several different methods, some of which are much more difficult than others, some of which where they watch the color of the star as the planet goes around it, and as the planet tugs on the star, causes it to move towards us or away from us, it'll make the color of the star shift to the blue, and back and forth. You can find exoplanets that way. Another way, you can get a telescope with incredible magnification and actually try to take an image of the planet, and you can use these things kind of like they're not really a solar filter, but they block out the bright light of the star itself, and you see just the dim light of the planets that are near that. Now, those are very hard to do. They've done just a few like that, nothing like the majority of these, but the vast majority of these are done by something called the transit method, where luck, that planet happens to pass right between us and that star. And so while it does that, it blocks a little bit of the light of the star. That's called the transit. Next slide, please. Look at this. This is working. So let me do this and see. This is now we're going to try something really special, technical. All right. Now, so a transit, you can see, so if you look at the center of this slide, here is a star up close and personal. And that black dot that you see would be a planet traversing across the surface, and as it moves in front of the star, it blocks out just a little bit, tiny fraction of the light, well under 1% of the light is blocked by that. By the way, this is a actual transit. That star you see is the sun, our sun. And you can even, if you look closely, you can see sunspots on the surface of the sun. That planet that's blocking the light is Venus. And it occasionally has a transit. So this would be what you'd see up close looking at a transit. Now, normally these stars are so far away, you don't see anything but a point, just a dot of light. There's no image. You don't see a disk. You don't see sunspots. You don't see anything, and you don't see the planet. All you see is the planet start off a little brighter, and then as the planet moves in front of the star, it gets a little dimmer, and then that lasts for a period of time, and then it gets a little brighter. And the graph you're seeing on the right is a graph of the brightness of the star. So if you actually were to take a little measuring device, which I'm going to show you how to do, and measure the brightness of the star, and keep recording, taking a bunch of measurements, you will see that the brightness of the star, when the planet doesn't block any of the light, you're up here because the planet is off the edge over here. And you can see it starting up there. And then the planet comes on and starts blocking some of the light. And so that's where you see it gets dimmer, the brightness drops. And then it makes this kind of a little bit of a bowl shape at the bottom. And we'll talk a little bit more about that. And then it moves off the right edge and the brightness jumps back up to where it was. That's what a transit is. And you could do measurements to see that change in brightness from the brighter to falling to a kind of blocking as it moves across the face of the star. You get a little bit of a shape, and you'll learn why. You get a little bit of a shape in a moment, and then it leaves. So that's a transit. That's all it is. That's the whole thing. You're now an expert. Okay, get ready for the test. Now, next slide, please. Uh-oh. Oh, that's true. It might require the animation. Look at that. Woohoo! No, it was our illustrious president figured it out. Okay, thank you. All right, so now here's something else to think about with exoplanets. They come in a range of different things that matter. And those are sizes and orbits. So it would be kind of intuitive that if the planet was bigger, it will block more of the light of the star, and it'll make the star get dimmer. You'll get a bigger change, it'll drop more. And another thing is the orbit. You may know that Mercury takes a very relatively short period of time to go around the sun. So in our year, it makes multiple laps around the sun. And the further out the planet is from the star, the longer it takes to go around the star and come into the position to block the light. And the rarer it would be. You'd have to wait longer to catch it passing in front of the star. So these are two things you want to know about because you want the easy one to do, right? You want the big planet block out a lot of the light, change in brightness, and you want it to be near the star so that it makes a lot of orbits so that you get a lot of chances to see it. So a big planet that is up close to the star is called a hot Jupiter. Jupiter because it's big, hot because it's close to the star, like Mercury is close to the sun, and the Mercury is hot. So this is a plot. Every one of these dots you see in here in this graph, the blue and the yellow, are dots, are confirmed exoplanets, and they're arranged in a specific pattern. Across the bottom is how long their year is in days. So over here on the left of the graph, you see 1 day is their year. Goes around, the planet goes around every day. So their year is very fast. They would have 365 years during our 1 year. And then here are the planets that are 10 days to do a year, lap around their star, 100 days. Of course, we're like 300, so we're out here 1,000 days. So, and the planets that are down at this end, the left end, give you a lot of chances to see it. So because you know, because you all live on Earth, you step outside, half the time it's day, and you can't look at the stars. And then you step outside at night and you look up in the sky, and half the time it's cloudy. And so a lot of these things, like, you know, if it was going by once, very often, half the time it's going to be daytime when it does a transit. So, and half of the remaining half, it's going to be cloudy. So you want one that has a lot of chances for you to catch it so that you can actually see that drop. So this is, you want the exoplanets that are down here. The other thing you care about is the size of the planet. So the bigger planets, the bigger Jupiter, Saturn kind of planets, block more of the light, which means it'll change the brightness of the star more. That makes it easier to see. So those are the two things you care about. You want them to make a lot of passes in front of the star so that you have a lot of chances to catch it. And you want it to be big. And so, of course, here at 1, this is 1 Earth size. Here's the size picture of the Earth. Here's 4 times, this is a logarithmic scale, 4 times the size of the Earth, which is the size of Neptune. Here's 10 times the size of the Earth. This is the size of Jupiter. So what you really want is these easy to observe planets, which will be the ones over here, which are many, many orbits per year for our years, so that you get a lot of chances to see them. And way up here in this corner, you want it left and up to get you the ones that are easiest to see because they give you a lot of chances and they make a big signal so that they're easier to detect. Yes. Yes. No, because Kepler, who makes most of these is a Kepler. So this is not the complete list. This was what Kepler had taken up to July of 10 years ago. And but of course, Kepler, it's easier for Kepler to see Jupiters than it is for Kepler to see Earth-size or Mercury-sized planets. So there is a selection bias. So you're not gonna, not only is it harder to see, but of the planets, exoplanets that we have seen, more of them tend to be bigger than smaller, which would make perfect sense because it's easier to see. And also, more of them will be closer to the star because they'll give us more chances to see it. So the chance that you happen to have your scope out and you're taking data when it goes through its transit, better chance. So you're playing the odds. It's like Las Vegas here, and we want that win. So next slide. Okay, so now I'm going to cheat on Las Vegas. I'm going to make it easy for you. There's a place you can go to called ETD, or it's actually been absorbed into yet another database, but there's actually a number of these databases for exoplanets where they've already gone out and they've found and categorized these exoplanets. And you can go into them and pull up a bunch of the information you want. And it'll tell you, here's a name of an exoplanet. And I can hardly see it with my bad eyes from this distance. And here's how long it takes for it to go around its star, 2 days. And by the way, this one is HD 189733. So which is, HD is for Henry Draper. It's the name of the people who built the catalog of a bunch of stars in the sky. And this happens to be their star 198377. But what's really useful in here is this database, you're able to put in your location on the Earth, and it will then tell you when every transit of that exoplanet is going to occur for the next year. And it'll tell you, is it going to be in the day or the night? And it'll tell you also, will it be 20 degrees above the horizon? Many of you who do astronomy enjoy or know that you want to look at things that tend to not be right on the horizon because the atmospheric turbulence is really bad and it obscures the planets. So what you're going to do is you're just going to pick from this database which planets to go look at. And it also has coordinates like the right ascension declination, so you can find it. And you just punch it into your telescope kind of thing, and it'll point at it. All right, next. All right, here is the hardware I took my data with. That is a 6-inch telescope. This is an 8, but you could have gotten data on the same target I collected data on with a 3-inch telescope if you had one. You do need a telescope that will track across the sky, and I'll explain why. But it does not need to be in a dark spot. This was you saw during the introduction slides. They put up a brightness sky scale of the Bortle scale, and where I live, it's a Bortle 6. So I live in a bright suburban area, and so it's a bit worse here in orange. Anza is a Bortle 4, so if you go out there, Anza is substantially better skies, darker skies than I have at my suburban backyard site. So you will also need, in addition to a tracking mount, as I've said, you could possibly get away with a color camera, but you need a monochrome camera preferably, because it minimizes the effect of color scintillation in the sky, which will add noise into the picture. It makes it easier if it's monochrome, and preferably an astronomy camera. So there's that little red thing you see on the end there is an astronomy camera. It was a couple $100. But you can get them for, closer to $100. So they cost a little bit of money. You could go ahead and try it. If you have another kind of camera, a webcam or something like that, you could try that also. But then that camera is run by a laptop. So that's the whole setup. It's a tracking telescope with an astronomy camera, and that's a ZAO 170. Type. And then this is just a bottom of the line laptop camera. So that's the hardware you need in your backyard. Next slide, please. Thank you. And then you need some software. Now, I used a piece of software called Nebulosity 4, which I don't believe is even in existence anymore. So, but first thing you need is a piece of software that runs your camera. And by the way, most cameras come with a piece of software that run the camera. And they will allow you to set things like how long is the exposure time, the shutter time on your camera. And you can tell it take some number of pictures. And it'll give you it'll put up each picture as you take it, because I'm going to tell you, this is a marathon thing. You take a lot of pictures, and I'm going to show you how many pictures you need to take. You don't have to go through them all, but this, by the way, is right there. If you have really sharp eyes, that's the dumbbell nebula. So these are, and that star right there is the HD exoplanet star. So it's in the center. No, I apologize, but my cursor is not visible on my slides. So sorry. But it turns out you don't even need to know which star it is, because in the next slide, the second piece of software you're going to use is called Astro Image J. Now, some of you may be familiar with this. It's a piece of free astronomy software. You just type in Astro Image J, Google, and it'll take you to the website and you can download it. And it does something called plate solving, which means you just give it a picture like this picture right here, and it comes back and it tells you what location that is in the sky. It'll actually, if you click on some stars, it'll tell you what those stars are. It'll give you the HD designation of those stars. And what this software will then do is it will actually measure the brightness of that star. And it'll compare it to the brightness of some other stars that you pick in the picture. And that comparison then forms the basis of the measurement. It's going to say that star, and oh, by the way, you tell it how bright that star is. These stars, which you, by the way, can go to Stellarium, a free software package you can also download, and you can look up some stars around where the star is that you are going to collect on, and you then tell it what the brightness of those stars are. And it will then go through and do all kinds of amazing things, like it will do a relative brightness measurement. So it will then it'll be comparing this star to this star, this star to this star, this star to that star. And that difference will then generate that little curve. That curve will also go through, it'll remove sky glow, it removes all kinds of crazy stuff that this software is actually used by professional astronomers. Type of application too. And so it'll generate that little curve you saw and actually do what's called a transit model. So next slide, please. So I told you it was going to take time, lots of pictures. So this transit, which by the way, the Exoplanet Transit Database website I sent you to first, will tell you how long these transits are. This is a 3-hour transit. So this is you will have to take data for 3 hours. So this was taking 10-second pictures of that one place in the sky for 3 hours. That's about 1,000 images. You're not going to wade through 1,000 images or do anything with it. By the way, the software, you just direct it to this piece of folder with these pictures in it, and it knows everything to do. And it will then, and if you see in this graph up above is actually the output of the Astro Image J. It has these little dots here. These are groups of those pictures averaged together, about 11 in each little dot. And so, and what you see is they bounce around. That's because the atmosphere has sky glow and all kinds of twinkling from turbulence. And it will average them all together, and it will fit a curve to this data. And this is the transit of that you have then recorded. And this is, by the way, exactly how professional astronomers do this type of thing. They take a large number of images, they average them together, and they use a computer model, shape fit, to the data set. Next slide, please. Okay, this is one of those fancy. Yes, click on it, and then this. All right. So now this is going to tell you how the software actually figures out what the heck is on here. On the top, this is a star, and you notice, by the way, it was darker on the edges. And by the way, stars are darker on the edges. You may not know that, but if you actually had a telescope and you looked at the sun with a filter, please, it's not with your eyes, it appears darker on the edges. And depending upon how the planet, how big the planet is, it changes the shape. Oh, so down here is the transit curve. This is the planet. This is the location of the planet in that picture. And so I set it to loop so you have a chance to, you're going to have to see this a couple times to get it. So depending upon whether the transit crosses the top or right across the middle, you'll get a different shape in your curve. The software is able to figure that all out and tell you things like what is the inclination of the orbit of the planet as it cuts across it. And let's see, changes when we change the planet size. Oh, so as you grow the planet size, this is what it does to the curve. It makes it go down. As you change the inclination of the orbit, so across the top, now it goes across the middle. What if it went across here? This is what you get, a different shape. The shape gets broader. And so now they're changing. This is what's called limb darkening. So the edges of the stars are dimmer because the atmosphere is actually absorbed some of the light. And so depending on the edge darkening of the star, you will get different shape as it falls. And this, again, the software is actually able to tell you sort out all of those things from the curve that it generates, that it fits to your data when you take 1,000 images for 3 hours. Okay, planet grows means it dips down further. Planet changes whether it cuts just across the top or cuts across the middle. This is kind of not an obvious thing. Cuts across the equator. It gives a different change in the shape. And then the limb darkens. That makes it, as the limb darkens, it makes it rounder instead of squarer. Okay. Yes. So these are YouTube videos. You can, if you're really good at hunting things down on YouTube, these are done by professional astronomers explaining what happens to the transit curve as it's in different configurations and parameters. Okay, so if you can stop that, right? It's going to beep at you. Oops, okay, so this is the curve blown up bigger that I took. And so each of these dots is like, I think it's like 11 of the 1,000 pictures grouped together to try to make it less noisy, but even at that, they bounce around. But the software knows that our atmosphere scintillates, and so it knows that that's really a flat edge, and same out here. And then it follows the data down and draws the curve. And from this data, the best fit is this kind of round bottom. And so and it's all up in this tiny little font up here, but it's broken out here. This curve tells you that the exoplanet, the radius of it is about 16% of the diameter of the star. That's what it can get out of the shape of the curve. And you can go look up. Hubble, of course, has looked at this too. And so I pulled the Hubble value, which is also shockingly close. I mean, these are not just, oh, you're doing something kind of with the same steps that a real astronomer does. You can actually get some values that are pretty close to some of their results, as long as the stars are bright enough and the planets are big enough. You know, you can't go to as dim and small as they do. It also, from this curve, it gets the exoplanet orbit is 12.4 times the radius of the host star. So it compares the size of the orbit of the planet to the size of the star itself. And Hubble's number is like 9. So factor of, 30% off on that one. The first one was really shockingly good. The second one is more like what I would expect, something where you'd be, with a 6-inch telescope, you might be getting 30% errors, but you're getting 30% of what Hubble is able to get. I mean, that's just to be, a few orders of magnitude in the same couple orders of magnitude. And that this exoplanet's orbital plane is inclined 87 degrees. And they're The convention is if you're looking at the star and the orbit goes like around the star and it doesn't transit at all, never passes in front of it, that's 90 degrees. Oh, I'm sorry, that's 0 degrees. And then if it crosses the equator of the star, that's 90 degrees. So this says, this data, the software says is like 87 degrees of the line of for our line of sight, and the Hubble is like 86. So another just really kind of impressively good number. You can get some valuable results that's not just random number generator kind of results out of this. Next slide, please. Okay, then here's another one. Everybody likes to know. Is this one of those Goldilocks planets? Could little gray aliens live on a planet like this? So you can pull out a little equation where the temperature of the planet is equal to the, and by the way, you can go through like Stellarium, one of the free planetarium programs, and look up this star and find out its spectral class, which it's a K1 spectral class, and the temperature of a K1 class star is 4,875 Kelvin. So you can take the temperature of the star, and a little bit of math. A is the albedo, which is the reflectance of the planet. Now the Earth, I have no idea what the actual reflectance of this exoplanet is, but the Earth's albedo is about 0.3. So I'm just going to throw in the Earth's albedo there. It's just a number, but actually I plot it here versus albedo, where it's 0 on the left, which means that it absorbs all the light and doesn't reflect any of it, and 1 on the right, and that is where all the light is absorbed. I'm sorry, where none of the light is absorbed, then it's just reflected. And so we have the temperature of the planet, temperature of the star, the reflectance, the albedo, that's a fancy astronomer term, and then the ratio of the radius of the star to the ratio of the orbit of the exoplanet, which was one of those numbers, which I just gave to you in the previous thing. It spits out from the software. So when you stick those numbers in, you get this dot right there. And so the lovely temperature of this planet is a bit over 1,000 Kelvin. So that's, so room temperature is 300 Kelvin, give or take a little. So smoking hot inside of your oven kind of temperature is what that planet would be. Next slide. So here's an artist conception, and I believe this was done by another professional astronomer, where they did a spectra of the planet, and it is shockingly hot. It's 2000. If you convert your Kelvin into Fahrenheit, you're talking about 2,000 Kelvin temperature, 2,000 degrees Fahrenheit. It's raining molten glass at this temperature, which they can infer from the spectral shape that they took. And this planet is blue. So it's a molten blue glass rain on a 2,000 degree Fahrenheit hot June. But you can do some exoplanets from limited. Next slide, please. So some more beautiful posters for you to download from the NASA website. Okay, turns out that this type of test is rather insensitive to a bunch of things that normally screw the heck out of beautiful astronomy pictures. If your telescope is blurry because it's not super well aligned or it's not super focused, that doesn't matter, because the software actually lets you draw a little circle around the star, and it adds up all the light in the circle that goes well beyond where the star is. And it doesn't care whether it was blurred out or not. It's going to count it all up. And so it turns out that you are not vulnerable to a lot of things that people worry about when they're trying to take pretty pictures. But what you are vulnerable to is you can't saturate the pixels. So when it's giving you each image your 1,000. You have to periodically watch it, and you have to measure. And these pieces of software will let you go in and measure the how bright each pixel is in the picture, and you look at the brightest star pixels, and you make sure that they're not saturated, because as you look across 3 hours, you're looking through different amounts of atmosphere. And so the atmospheric transmission improves or decreases. And so you could easily start off and it would be not saturated, but as the atmosphere gets prettier, you get it, or less turbulent, and you could saturate it. That it can't deal with. So you have to, that's the one thing you have to worry about. So, all right, so that's it. There's work, there's complexity here, but even with your backyard and a small telescope, you can actually take data and come up with measurements that can get in the same ballpark for some of these brighter exoplanets that look like professional astronomers. See. Correct. You just go into your camera and you reduce. So the question was, thank you. The question was, if you do observe that you're getting saturated pixels on your stars, what can you go in and lower the shutter time, make the picture shorter so it doesn't collect as much light and therefore doesn't saturate? And the answer is yes. That's exactly what you do. Question number 2. Can you just randomly point it at things? And well, so when it does the analysis, it'll generate just one target. Oh, you again. So he's asking, can you use this software to do a random search where you point it at someplace in the sky and you say, look at all those stars, tell me if any of them are winking with little exoplanet transit curves. And the answer is no, it's kind of manual. You have to tell it which star is the target and which of the other stars nearby you want to pick as the reference stars that you're telling it are not winking. So it has that kind of, it has that limitation. Other questions? No, let's see. Reza, do we have any online questions?
Yes. So the questioner wants to know if you have experimented with long-term observation to measure elliptical orbits.
No. No, I am, to me, this was one of those, I would really like to try to see if I could ever measure an exoplanet myself. It was like a personal goal kind of thing. Now, many people would turn this into a long-term project and do either what our last question was, which is search for new exoplanets or look for elliptical orbit data. But I have not done any of those or either of those.
Okay, thank you. That was it online for now. Back in person.
Last call. Questions? I will turn it back over to the fearless leader.
Thank you very much. That was an excellent talk. We really appreciate that. Raisa, have you got any last comments?
Well, actually, we just got a question online if we could have our speaker back.
Oh, absolutely. He has not wandered too far away.
So the question is, with the setup you showed in the presentation, what do you think is the best case resolution of magnitude changes?
Could you go to pull up? Do you still have the slides or can you get out? So, well, here, I'll just take a guess. I don't know exactly what the answer to your question is, but I will tell you that almost every exoplanet when they like you go into the database, and what they will tell you is not the percent change. They will give it in milli magnitudes. So 1,000th of one magnitude number is what, and so I believe this one was 25, 26 millimagnitudes. I might be wrong, but that's my vague recollection. So I would guess, and you could see from the curve that I took that the points were, yeah, there was spread in them. You could see noise, but it wasn't just all over the map. And the noise was much smaller than the size of the dip. So you could probably go to half of that or a quarter of that fairly straightforwardly with even that 6-inch aperture telescope.
Thank you. Another questioner has actually added a comment to that, saying that in these type of observations, we basically use flux rather than magnitude for observations. So the change in flux is what we're after. Yes. And then there's another question. Do you flat filter your images?
No.
Okay.
Yeah, so the those other stars that you identify, I think I dark corrected them, but I didn't flat field them because you're doing a relative measurement, that tends to correct that. A whole host of errors actually are corrected by that relative measurement. So no, I didn't. But if you're trying to do, in far smaller magnitudes changes or percent changes of light, then yes, you would absolutely have to do that. In fact, that probably might not be enough to do even that kind of thing. So that's my response.
Okay, great. Thank you very much, Steve, for a wonderful presentation. Totally enjoyed it. And we're looking forward to OCA members giving us their curves for their exoplanet discoveries.
Any last questions before we let you all go for the evening? Oh, and Steve will be around for a while, so you can ask him questions if you're here on the ground at any rate. Okay, well, thanks again. We really appreciate it.
Okay, I would like to thank everybody for attending in person or online. Online audience, we're saying audio.